Hi everyone, today we will look into another component of the power in CMOS, and that is the short circuit power. So when the very first video, the last two videos I did, they were mainly focusing on dynamic power. And the dynamic power was really the power that is used in charging this capacitor over here and discharging that capacitor. And I mentioned that overall total power is combination of that dynamic power that I mentioned, and then another component is the short circuit power. Third component is leakage. So today we are going to talk about this one. It will be a short video, I think. Let's see. So this is our best friend, CMOS inverter. You apply a voltage, it goes out. I keep repeating these things, I know, but it's good to repeat things always. You never know who's gonna watch this video. When input is 0, steady state, settled at 0. Steady state means it's settled finally at that state. 0, PMOS is on. When it's 1, NMOS is on. So this is the input waveform. When it settles, when I say settle, it stays constant. Things get simpler, okay? It's that particular state of the transistor that we are in. But this transition is interesting. It's interesting because now both PMOS and NMOS are going through a change. A change in the area of operation or region of operation is happening. And that's a little bit tricky to understand that. So bear with me, I'll explain that because that thing is related to this power. This power is when this is on temporarily, momentarily during the transition, and this is on. In eventually in steady state, only one of them is on, so you don't have a path of current from all the way down. This is off or this is off. But during the transition from 0 to 1 and 1 to 0, momentarily, for a very short period of time, PMOS is on and MOS is on, and that's an opportunity for this voltage to drive a current all the way to ground from here, which is not what we want, right? It's an ideal switch. It's never supposed to be this on and this on at the same time. They're supposed to be on and off. That's the whole philosophy of 1, 0. So question is, how current when these two are on? Okay, in a very simple way, without going into region of this is a cutoff region, this is linear region, or this is saturation region, without going down, you can think of that. Okay, PMOS as input is 0, it was on, and as we're trying to go to 1, NMOS want to be on. So of course there is a period, a little bit tiny bit when the PMOS is on and NMOS is on, somewhere around this time. And that's it. If you're happy with that understanding and you think that is enough for you to move on, just move on. I think that's fine, totally fine. But if you want to understand a little bit more, okay, how you can reduce it, you can obviously think that, okay, reduce this transition period. This time, if you reduce this when both are on, that will be good for this. And I think even that one is good enough. You can move on. What I'm going to explain a little bit more is, I don't know if you remember the transistor operation or not. And in that transistor operation, the way I explain and then the way you will hear in every or read in every book is something like this. Okay, transistor is off and MOS is off. You apply a little gate to source voltage because there is a threshold voltage. If VGS is greater than VT, our transistor is on. Okay, when transistor is on, which region is it? Saturation, where it is supposed to be a constant current, or a linear region? Remember this equation. Sorry, I'm drawing it too small. Where trans rarely remains constant, and here is we have almost linear region, where this is VDS, the drain voltage. Drain voltage, keep in mind, the drain voltage here is the same as the output voltage. So this is drain voltage and this is the current. Looks like I drew too tiny. Okay, let's do that. So what happens is, and this is what I said, okay, you start with off, your VGS greater than VT, transistor is on now. As now you are increasing the drain voltage, this voltage, and somehow you are increasing this one. This will start pulling the electrons in the gate, so you will have a current flowing in the NMOS. But then I said, okay, linear, when this VDS eventually reaches a critical point, and I said it's VD-SAT. Again, there I have a whole video on VD-SAT. So if you don't know, if you're confused, you can watch that. But that is a particular value of drain to source voltage, which we call VD-SAT. At that point, if we increase VDS more, transistors go in a mode where increasing VDS will not have any impact on IDS, it will stay constant. So this is saturation region. So we told that, okay, transistors off, go into linear and saturation. But you need to keep one thing in mind. This is good for explanation. But when you look at inverter, actual, and I think I explained this in a video too. Before NMOS was on, PMOS was on. So the moment NMOS is turning on, this voltage at output is already at VDD or close to VDD. So the sequence of operation, the way it happens is, even though we explain as something like, okay, off to linear for NMOS I'm talking about, and I guess same is for PMOS. Saturation. Actually, what happens on an inverter case is it's an off, then goes into saturation. And a lot of I used to be confused with this one too when I studied these things very first time. And then it gets into linear. And this is where it settles finally, steady state. Okay, so this saturation is the kind of during the transition happens. Now, digital logic works between this and this. In digital, we don't want to stay in this one. In analog IC designers, they design their circuit to stay in this one because this one gives them an interesting region of operation. This is not interesting. Things have settled down. This is where things are changing, and transistor provides a good gain to the input voltage, so the input signal, and that's why they are interested in creating that gain, some amplification, something different. So this is the area of region for analog, and for us digital folks, we're not interested. We don't want transistor to operate in that. We want to, ideally, if it is up to us, we would skip that. Okay, so that the reason I explained that, because where I'm getting into is this the same thing. Input was 0, PMOS was on, and this blue is showing kind of PMOS change of operation. Okay, what happened as it goes to 0 to 1? After a certain voltage, it is first in linear. Sorry, I think why I put it the other way around. Should I change it? What do you think? Let's change it. Because you'd probably be flipping your, yeah, okay, I don't know what I was thinking. PMOS is on, and here let's say PMOS was in linear up to this point. Then it went into saturation. Then it's off. In the same way, what happens to NMOS is was off initially. As soon as you hit this voltage, this is the VT. After that, since our output voltage is already at VDD, so it goes into saturation and then it's off. I think I explained it a little bit more, so maybe this is good here. We will get back to this. So when it's off, transistor off, VGS gate to source voltage. In NMOS case, this is your gate voltage, this is your source voltage, this is our input voltage connected to both PMOS. This is our output voltage. Okay, this is off region. And when gate to source voltage here is greater than that threshold voltage, now we are turning on the transistor. So if you see linear and saturation, both have this thing common. It needs to be greater than threshold voltage for the transistor on. But in order to differentiate between linear and saturation, in the linear region, in the saturation region first, let's talk about, because PMOS was already on, so this, just when we were turning this guy on, this node is nearly at VDD voltage because this was on. So we have this situation where gate to source voltage is more than VT and drain to source voltage or output voltage. This is, sorry, not this one. This is wrong. Drain to source voltage is V out. This voltage is greater than that VD sat. Again, VD sat, I have a whole video. I will not going into detail of that. But think of this as a lower drain to source voltage. Transistor in is in saturation, and then when you keep lowering VDS, eventually it gets lower than VD sat, then it gets into linear. So that exactly this thing is happening. It's off, goes into saturation, goes into linear. This goes into linear, saturation off. And when you go back into PMOS, the same thing. PMOS, NMOS starts with linear, goes in saturation, and turns it off. PMOS start with off, goes in saturation, goes into linear. Okay, you hope you understood that now. This is the time, or here the same time over here, when both N and P are in saturation. So both are on. So you can think of that this short circuit is really short circuit supply to ground. That's what it means. And there's no capacitor. Well, there's a kind of capacitor here, but this path is the least resistance path. So it's not going to charge that much capacitor here. So short circuit power is proportional to how much current P and NMOS have. ID set. Saturation, current in saturation. And if you remember, current in saturation depends on, there's a constant there, but width over L, VGS minus VT power of 2, square of dependence on this one. So if you want to reduce short circuit power, what you do, reduce this time and or reduce the saturation current somehow through playing with these one. But these will also, if you start changing them, these will also decrease the current the linear region when you are in a steady state, and you don't want that. A good current in a linear state is good. That means transistor will be faster. Okay, so this is important. Higher current in linear region for NMOS, this is when it's in linear region. The higher current that fast means it's faster transistor. You can run at a higher frequency. So how you can, so I'll already look at, okay, through current and through short circuit, but there's another important philosophy here.